Thanks everybody for showing up. We've got another demo. It's been a while since we've done a compiler demo, and so it's time to do one. What I'm going to demo today, this is not a functionality demo. It's a performance demo, right? Because rather than working on new functionality, we've been going in and reworking the back end of the compiler, especially for the past several months, and making various parts of it more serious. Because you always have to do things like that as you go along the spectrum from prototype to production. What I'm going to show is today we're going to be compiling something that's approximately the same program that we were compiling in the last demo. It's about 33,000 lines of code. It does the same thing. There's been some minor refactorings of it, but nothing that really matters. And because this is a performance demo, I should specify the hardware. This is running on a Razer Blade 14-inch laptop from 2015. The CPU is an Intel Core i7 with the numbers you can see on the screen at 2.6 gigahertz. And I'm streaming off it, which takes about 6% of the total CPU, and which is why I am streaming in a lower resolution than usual. Because if I stream in a higher resolution, the streaming takes proportionately more CPU and messes with my numbers, which I don't want. So that is the situation of our demo. Okay, so I didn't realize that let me make my face really small so it doesn't so much intrude on the slides. I don't really, maybe that's small enough. We'll see. I didn't think about that. All right. So, last time we demoed, I sort of showed that it took a couple seconds to compile this 33,000 line program. And it was, approximately the same compiling both with the C backend or the LLVM backend, but that the C backend last time, if I remember correctly, was actually a little bit faster. So for review, I'll just go back and do the C backend. This is the build time program, right? Remember, we don't use a make file or anything like that, or a Visual Studio project file. We have a program that builds our program, and that makes the system very powerful. This is part of the program that builds our program, and it's just specifying there's some enum for what backend you want to use, and I'm going to use the C backend. This was all demoed in detail. I don't remember which demo, but a while ago, where I show what all the enums are and what kind of options you can set and all that. But so for now, we're just using the C backend, and I'm just going to compile the program. And that took a little while. The total time of compilation was about 1.68 seconds. Ignore all this stuff. It doesn't matter. You know what? No, I'm not going to rebuild the compiler. Take that out. Just ignore it. So the things we care about are stuff like the total time, the back-end time spent compiling C, which is quite long, 1.5 seconds. Whatever. We're not going to care about these numbers too much for C. We're going to care about them for LLVM because they got better. But anyway, this is just to say that the state of the art last time was to do 33,000 lines of code in about 1.7 seconds. It was a little longer, I think, because we sped some things up since then. All right, so I can now demo that LLVM goes substantially faster than that. Well, let me not get ahead of my slides. Yeah. So it goes substantially faster than that. Actually, so right there we got 1 second, but I think things weren't fresh. So if I do it again, I should get an even better number. So 0.93. We're taking a little bit of a penalty because I'm streaming. So when I do this timing and I'm not streaming, it averages around 0.88 seconds, which is a lot faster, right? That's in the neighborhood of twice as fast, broadly speaking, as the C compile time that we have now. And that's the total time, including our front end, right? So we do all this, lexing and parsing and type checking, and then we pass that information to LLVM, and that process of passing it to LLVM and then waiting on LLVM to respond takes about a half a second. Then we pass it to the linker, which is link.exe, which is Microsoft's linker, right? And that takes about a quarter of a second. This number is just these two numbers added together, so all the backend time. So, and then our total time is just our backend time, which is not indented, plus our front end time, which is not indented. It might be a little confusing, but you get used to it. Anyway, so 0.93 seconds. So we're now under 1 second. That's a lot better than before when we were at like 1.7, 1.8 or whatever. Right, so here's the times to 2 significant digits. So how do we make it faster? Well, we did a few things. We cleaned up our feeding of the LLVM API to require a little bit less data structure manipulation in order to do the translation. So in some cases, we were able to change our internals to create the kinds of data that LLVM wants earlier in the pipeline, right? So then we don't need to cross-reference to get it later. Also, this is something that affects all our backends, not just LLVM, is that I optimize the generation of the bytecode a fair bit. Now, if you recall, we have our own internal representation that we can run in a bytecode interpreter, and the process of compilation involves generating bytecode instructions starting with the syntax tree of the program. And that process of going from syntax tree to bytecode, I spent some time optimizing and reduced by about 16% the number of bytecode instructions. And so everything later in the pipeline automatically got 16% faster approximately, give or take. Different things take different amounts of time, but you can imagine that if you pass 16% fewer instructions to the back end has maybe 16% less work to do. So you compound these two things and then a lot of other things that are too small to list, and that's where this speed up came from. So that's all great. However, as I said last time, I didn't think that LLVM was ever quite going to be fast enough because I want, for reasonable sized programs, close to instant compilation. And I don't see why we shouldn't have that because I think it would be very good for workflow. So I spent a lot of time doing a new backend, x64. This backend goes directly from the syntax tree, it goes directly from bytecode. So we go from syntax tree to bytecode, just like before, and this goes between bytecode and x64 machine code. It outputs a binary object file, .obj, in Windows. It does not output assembler or any textual format at all because we want it to be fast. So let's run this, and it might take a couple runs because again, it's maybe cold at this point, but that's not too bad. So our entire time to run now was 0.38 seconds. The x64 backend actually took quite, no, that's expected, right? Do I want to break these numbers down? Let me see what my slides say. Yeah. So here's sort of the numbers printed bigger where you can see them. The total time to compile tends to be about 0.36 seconds. Again, we're taking a little penalty from streaming, so we came out at 0.38. If we run a few times, we'll see if that's consistent. Yeah, 0.37, 0.39, So not streaming, we hit around 0.36 with a little bit of variance around there. Now, the front end time is about the same. It's about 0.16, 0.17 seconds. Wait, is that right? Yeah, 0.18. It's in that neighborhood. It's the same as for LLVM because the front end does the same amount of work. And now the x64 backend takes over. So that is much faster. x64 plus linking in this case is 0.15 seconds, whereas for LLVM is 0.69 seconds. And just the x64 backend by itself. So, and the reason this makes sense to measure is because the linker is Microsoft's linker. We're not in control of that linker right now. We can't make it faster, apart from feeding it less information, which I have attempted to do in the x64 backend. The x64 does as much of its own linking as possible without emitting symbols. It takes actually 0.03 seconds to output the machine code for the whole program, compared to LLVM's 0.47 seconds right now. And again, we may be able to tighten up this LLVM number, right? We might be able to make it substantially faster, but we can also make this substantially faster. Like I think I can cut this 0.03 seconds at least in half to 0.015. Is essentially instantaneous on the scale of things that this compiler is doing, right? So if we want to lay that out in a table so we can see them both, then we see sort of the two use cases that I've talked about in previous demos. If you want to generate optimized output code, because our x64 backend, part of the reason it's so fast, in fact, one of the main reasons it's so fast, is because it's not trying to optimize at all. It's doing a very literal translation of, our intermediate bytecode to x64 machine code, and when you do that and you don't monkey around, you're just basically emitting bytes like full on, right? So that's why it's not taking much time. But of course, you don't necessarily want to ship that code. That might be fast enough for you to work with and debug and do your day-to-day work in. But shipping code, you want to be as fast as possible, right? So here, we sort of have two different use cases. So we can use LLVM to generate optimized output machine code and to have broad support of many platforms, right? Because this backend only works on x64 CPUs, which is a lot of CPUs, right? That does include both PCs as well as consoles like the PlayStation 4, the Xbox One. But there's other stuff it does not include, such as ARM CPUs, like many mobile platforms, right? And many embedded CPUs and stuff like that. So to target that stuff, you would use the LLVM backend, and you take a total compile time of around 0.88 seconds, right? These two numbers at the bottom, I didn't say backend, but this is the backend with link. This is the backend without link. So this number includes time that's the same between both, right? So full compile time, again, is 0.88 versus 0.36 seconds, and then so on. In this slide, I actually compare things directly. So the part of the backend that we can control with x64 is about 16 times faster than the LLVM backend, right? However, we do have to wait on the Microsoft linker right now, and I don't know why linkers are so slow, but they are slow. Even the linkers that people think are fast are abominably slow for the amount of work that they do. So it takes far more time. It takes 5 times as long to link the output of the x64 assembler or machine code generator than it does to actually generate that output, right? Which is ridiculous because I do tons of linking in the output itself. So I don't know what this thing is doing. It's crazy. There's ways around that, which we'll talk about in a bit. But so our 16 times advantage, once we include this 0.15 seconds that we can't control, drops to 4.6 times faster, which is still a lot faster. And then I didn't divide out this number, but this is better than, what is it? Let's see. Windows, Calc, 0.3 or 0.88 minus 0.36 divided by 0.88. So that's 59% faster. Oh, I can't edit right now. Anyway, so, wait, I didn't want that. I wanted 0.88 over 0.36 because those are the numbers we're comparing. Clear, 0.88 over 0.36. So including the front end time, we're 2.4 times faster. Right, so this is 2.4, this is 4.6, this is 16, right? So that's pretty good. It's very, very promising. I didn't talk about what program we're running. It's the same thing that you saw before, right? So here, the last time I compiled it was with the x64 backend, right? So, yeah. It took 0.03 seconds to generate the machine code. Here is at least part of the machine code that we generated. Again, it's playing music. Oh, I don't have the PC sound on, but it's playing music. It's rendering a 3D mesh from the witness. It's got a little bit of editor code in it. It's a non-trivial amount of code. Just like I demoed last time. It's exactly the same, right? But the point being, we compiled that whole 33,000 line program in 0.39 seconds. And that number is going to get faster. Now, So our total time here was 0.36. 0.15 of that, like going on half of that time, is waiting for the Microsoft linker, which is sort of the last dependency in the chain that's not under our control, right? So just by ditching the linker, we could go from 0.36 seconds to 0.21 seconds ostensibly if we magically replaced it with something that took zero amount of time, right? And that would be a 42% speed up over what we have just by doing that one thing, which would be huge, right? 42% is not funny. And we'd remove the last dependency on platform installed software, right? So right now, you could install the binary for the compiler and just run it, but still, no matter what backend you use, it still has some system dependency, right? So if you're using the x64 backend or the LLVM backend, we need a linker, usually the Microsoft linker. If you use the C backend, you need a C compiler and linker, right? So having that kind of dependency is not that great, right? It reduces the agility of deployment. I prefer that you can just copy the binary for the compiler onto your machine and not even run an installer or anything, right? You could have it just on a network drive and run it from there if you want, right? Or on a USB key or whatever. So that we'll do in the future. I'm not going to do it as the next demo because I want to break from back-end stuff for a while. I want to do some front-end and middle stuff. But that is sort of the next big step to cut down the compile time. We should be able to cut this 0.36 seconds total time to 0.2 something or less. And that'll be great. All right. Let me do these slides out of order in a second, right? So if you want sort of performance numbers, oh wait, that's the wrong performance number. I didn't do the performance numbers I'm thinking of. Okay, let's do the slides in order. Now, aside from back-end work, I did some work on the overall structure of the compiler, and it's now structured to run more in parallel. Now, parallelizing the internals of this compiler is non-trivial. And I haven't done it for everything, and I probably won't do it for everything for a while, but I have fully parallelized the lexer and parser with a job system, much like the kind of job system you would see in games. And you can actually see the results in this output. Let me run it a few times and see what kind of numbers we get. So here it took 20 milliseconds. Perform loads, we'll look at this in telemetry in a second, but perform loads is how long it takes to lex and parse the entire program, all 33,000 lines. It took about 20 milliseconds there. This time we were a little warmer. We got a little luckier with thread scheduling. It took about 14 milliseconds. Windows does not give you, it does not spin up threads very fast, and it does not give you very predictable granularity over thread scheduling. So as we keep running this, it'll vary by some number of milliseconds. So that time it was 16 milliseconds. That time it was 16, that time, 16, we're getting consistent. 13 milliseconds, we really won the jackpot that time. The point is, we can compile that entire 33,000, or we can lex and parse that entire 33,000 line program. So converting it to the internal syntax tree in less than 1 frame time of a 60 frame per second game on a laptop. And the compiler is not even as fast as it's going to get yet, right? So that's pretty cool. I spin up about 6 jobs or maybe 8 jobs to do that compilation, and let's look at that because I want to show graphically what that looks like. But I just want to underline again, people out there think, oh, lexing and parsing is really hard. You have to use all these parser tools, and it's like NP complete, and programming languages as powerful as C++ are going to be inherently hard to parse, and the parsing is why C++ takes so long to compile and whatever. It's all garbage, right? None of that is true, right? Again, we can parse this entire program, 33,000 lines, and it's going to get bigger, right? Well, this number will go up a little bit, but in 13 to 16 milliseconds. So parsing, right, 16 milliseconds is nothing compared to the 0.36 seconds that this is taking, right? 13 milliseconds is 0.013 seconds. So parsing takes like no time. This is already fast. Whoops. I ran the wrong thing. It's already fast, and parsing takes no time compared to that. So I just want to beat that in because people don't get it. People don't know how fast computers are. Computers are really fast, right? So the fact that we can do all this parsing work here this fast also means that the rest of this front end time is going to be able to come down as well, which is going to bring our compile down time down further. Okay. Let us go into telemetry. Last time, I have a previous run here that I generated with telemetry, which, as I demoed previously, is a visual performance analyzer. So you basically put hooks into your program, and then it gives you a graphical representation of everything the program does. And I'm not going to go too deeply into what the program does, because you can look at a previous demo if you want to see. Here, I want to make sure I telemetried the right thing. Let's do it again. Let's do a fresh telemetry because I want to make sure I was set to x64. So here we're set to x64. We're going to run telemetry. The time we take to compile is going to be a little bit higher than with the release build of the compiler because, these hooks that we spend reporting take a little bit of time. They don't take a huge amount of time, but we went up to 0.42 seconds instead of 0.37. All right, so that will have put a new thing over here. Let me close the settings so we have more screen space. Okay, so this is 12:25 a.m. This is the one I just ran. So this for sure is running. Let me close the old one even. This for sure is running in x64 mode. You can see our timeline goes to 400 and something milliseconds, which matches the 0.43 seconds over here. And let me talk about what's happening here. This sort of very busy area on the left, before we get to all this red, is the compilation and running of our boot program, essentially, the thing that does our build, like the equivalent of our makefile or whatever, the program that I'm using to set which backend we use, among many other pieces of functionality, right? So that is running for about the first 40 milliseconds or something. And then we start compiling the main program. And remember I said parsing happens in about 13 milliseconds and it's parallelized with a job system. This is parsing. So let's go zoom in for a second. What happens is first, so right around here is when we start compiling the main program. And the first thing we do is we load the preload, which is like some stuff that the compiler needs to load no matter what it's compiling, like definitions of structures for communication with the compiler and whatever. And you guys have seen this in a previous demo. The types, like when you talk about the type introspection in your program, all that stuff is defined in the preload. So this is parsing and lexing the preload, and this is doing semantics and bytecode generation and all that. Once all that's done, which takes, I don't know, from like 23.5 to 24. That takes about a millisecond to do all that, millisecond and a half. Then we're ready to compile and run the main program, which we start doing here. So we load main. At first, we can't parallelize our parsing very well because we only have one file. Right, we have this file main, and it takes care of loading all the other stuff that we want to load. So we load main, we parse main, we run main, and then main starts adding all these other files. Fortunately, that is not much of a bottleneck. It takes 600 microseconds, which is less than 1 millisecond. And here, now all our jobs are spun up, and main has said, let's go look at main for a second. Oh, my font is really big here. Main has all these imports in it. That's the main way that it gets files, right? Is just says import basic, import print, import GL, blah, blah, blah. And then here's all our, so those imports kick off loads of things in the modules folder. And then these load directives kick off loads of stuff in my own source folder. Now we start to see those files, like here's basic, which is a module. Here's like my own source. Starts to get kicked off, and this is all in parallel. So thread 3, 4, 5, 6, 7, 8. Remember, this is a timeline. So as you go left to right, time is passing. So all these cores are highly utilized. You see they're not really blocking very often. Here we have a core that's stuck on something. It's probably trying to grab a mutex. I didn't log the mutex. You can log mutexes in here and stuff with telemetry, but because you maybe access mutexes frequently, that increases the overhead. And I wanted to give you a more accurate picture. So, once in a while we see stalls here, but the stalls are not that bad. And in fact, they can be improved, right? So the empty gray space is stalls. So we're really using all those threads very effectively. And that's why we're able to compile so fast on this machine, right? If you didn't, oh, you know what? Let's do this. I added a no jobs option, so we can run another thing. So we're doing exactly the same compilation, but we're saying don't turn on the job system. So we're going to compile everything single-threaded, right? So now it took 42 milliseconds. How much did it take last time? 15. So we're getting about 3x parallelism out of 6 threads or 7 threads right now, which is pretty good for something, especially something like parsing that builds a lot of data structures and does memory allocation and stuff. But there is room for improvement in that. However, I sort of feel like 15 milliseconds is fast enough, so it's not high on the priority list anymore, right? The rest of this 0.36 seconds is the target now. But there's room for improvement there. But let's go back and look at this. So this is the one I did without the job system. And here you can see there are many fewer threads. There's just these 3 threads, one of which is telemetry. So there's just like the main thread and the workspace thread for compiling. And now you can see perform loads takes a lot longer and loads all these files in sequence left to right. It's not blown out in parallel like before, right? So now this entire time up through 50-something milliseconds is parsing. But either way, it's still fast, right? I mean, that's way faster than most compilers will parse your program. So I just wanted to show that. I wanted to show that this is parallelized. Now, once we come out of the parser, nothing after that is parallelized yet. So I started working on the semantic pass, where we do type inference and stuff. That's down here. That is by far the slowest thing now in the front end. It is most of the time at the front end. It's the green stuff. And we went into detail about the green stuff last time that we demoed telemetry, which I think is in the previous demo. That takes 6 or 7 milliseconds at a pop, or sometimes 10 milliseconds for a file. So if I can parallelize that, then this long band of mostly green will start getting broken up and will look like this and be more vertical. We want vertical on this graph, not horizontal. So that is going to be a point of work. However, that's actually kind of hard to parallelize. Even though it's the main time bottleneck, I might do some other stuff. So this blue in here is the bytecode building, which is much easier to parallelize. I might do that next. x64 generation would be very easy to parallelize, but it's the fastest thing. It's 0.03 seconds, so there's not much point in that. All right, is that everything I wanted to say? So going back to that Lexington parsing number of about 16 milliseconds, so we parse about 2 million lines of code per second, right, on a laptop. So if you get into the realm of like, I'm doing 10 million line game engines and I want to compile that, you could compile that probably, assuming everything goes linearly, in about 5 seconds from scratch, non-incremental build, no build farm where you're like doing parallelism out to everyone's machine in the office. And in fact, it would be much faster than 5 seconds because you do it on a desktop machine with more cores and faster cores than this poor laptop that's 2 years old at this point, right? So if I parallelize more of the compiler, like the semantic pass or the bytecode builder, then we can get our front end time down from 0.17 seconds to something much lower. Now remember, I said before that, let's go back a few slides. If we get rid of the linker and output an executable, we could drop maybe as far as 0.21 seconds, right? But 0.17 seconds of that is the front end, which is mostly not parallelized yet. So let's say we can cut that 0.17 seconds in half, which seems reasonable. Maybe that's optimistic, maybe it's not, I don't know. but that cuts, that subtracts, let's round it up to 0.9 seconds. So subtract 0.9 from 0.21 and you get 0.12. So it is feasible that we could compile this 33,000 line program from end to end, non-incrementally, full rebuild, none of the jankiness that you get when you're doing an incremental rebuild and like things didn't really rebuild when they should have, or you get precompiled header problems, or you try to insert something at the top of your file and Visual Studio's stupid precompiled header system gets confused. None of that, right? Fully clean for this size of program in like 0.1 seconds. And then of course this program is going to get bigger, but 300,000 lines is a pretty reasonable size of a program for a game, for an indie game especially, and that'll probably come in under 1 second, especially on a desktop. So that's really great. Also keep in mind that when I say it's a 33,000 line program, this is without header files or any of that forward declarations or any of that C++ nonsense. So this is the equivalent of a substantially larger C++ program. I don't know how much larger, let's call it at least 45,000 lines. It depends on your programming style. Like if you're one of those people who does really small CPP files, then it's really the equivalent of a much bigger program, right? But it's some bigger C++ program, right? Okay, I think that is everything I want to say. So I'm going to take a short voice break and we'll do questions. I can pop this open while I wait for questions. I just like, let's go back to this one because we are on that one. I want to see the parsing in parallel. So keep in mind that this isn't right. This is just, I ran the compiler executable. This doesn't require your operating system to have like CMake plus Ninja plus whatever the hell Makeify of post-apocalyptic make. Like it just works, right? And again, that's part of the beauty of what we're doing is we're making things that just work. And because it just works, it'll work on every operating system the same way without you having to have a heart attack for 5 days every time you try to get it working on a new thing. Okay, voice break for a couple minutes. Intermission will resume in 5 minutes. I also want to Shift F5. Yeah.